Okay, what's up everyone? We got a good one today. Singular value decomposition. So this is, in a sense, a factoring result, but it's deeper than that in a lot of ways. You can think of singular value decomposition as something like a spectral theorem for non-operators. That is, for just arbitrary linear maps. Let me kind of give you the general idea of it before we start getting into the specifics, because I think it's actually pretty cool. So here is the gist of it. Now, I'm going to zoom in to make this drawing a little bit easier to do. For some reason, I'm getting some lag on my tablet. Hopefully that doesn't continue too much. Okay, so here's kind of the picture. So, for linear maps between Rn and Rm, everything works like this. Here's how it works. So I'll draw the picture. All right, start out, and I'm going to draw it like it's from R2 to R2 because it's hard to draw anything else. Here's the gist. I'm going to draw a couple of like little chunks here. Okay, and maybe I should draw these a little bit closer together. Let me do that here. Sorry guys, 1 second. Let me make sure I'm getting everything looking nice so it fits together really smoothly, and then we can actually, okay, here. This picture is important, so I want it to look good. Here's basically how all linear maps work from Rn to Rm. So the gist of it is that you could take, say, some basis vectors, say like they're unit vectors, right? So then you would have some kind of like a circle, like this is a terrible circle. It's not perfect, but it's close enough. It's a circle, you get it? Yeah? It's like a circle with radius 1, yeah? We're just going to look what happens to the circle of radius 1 since it basically tells you what it does to everything. That is, if you want to know what it does to any other vector, well, it's just a scaling of something on the circle of radius 1, right? So here's what happens. The circle gets moved over and rotated by a little bit. Okay. Undo that. Okay, here. I have to kind of, I'm not very good at doing these circles. Okay, so first you rotate, then you stretch. Okay, so there's some kind of a stretching factor that goes on here to make this into a weird little ellipse. All right. There's some kind of like a stretch. It's a terrible. Unfortunately, I'm not very good at drawing ellipses. I want to make that a little bit more pronounced, that it's stretched out. Okay, here we go. So it gets stretched a little bit. And it doesn't have to be like perpendicular to the axes or anything like that. It just gets stretched in some direction. And then it gets rotated again. So we just take what we had right there and we rotate it. That is, if I just grab, I'm just going to grab this piece just for convenience. And then I'll move it over here. And then let me see, can I just do... I have to erase a couple things right here really quick, but it will look much nicer when I get done if I just do it this way. Here, so I'll erase these axes just to make this picture clear. Maybe I should have drawn this picture before we started, but let me finish, then I'll tell you a little bit more about what I'm trying to say here, and hopefully it will all become clear. So, this is maybe a surprising fact. Maybe it seems a little bit weird, but if you think about it, okay, almost done erasing before I start talking while erasing and make some kind of a mistake. Okay, there we go. And here we go. All right. Bada boom. Okay, perfect. And maybe I should have rotated this even a little bit more. Somewhat unfortunate that I made these look like they go back to the same axes, but it doesn't matter too much. Basically, the gist of it is that all that ever happens for linear maps from Rn to Rm is you take basis vectors and you send them to some other vectors, right? So those new vectors, they could be whatever. They could be, some of them could be zero, some of them could be non-zero, and so on. Those are the new arrows that you have after you push it through the map. That you can get these arrows in this way is not strange at all. Essentially what goes on is you rotate them a little bit, these initial vectors, till they have like the same angle as the new vectors. You stretch them out by, dissimilar factors. It doesn't have to be like a uniform stretch, like it's just like a scaling. It can be a stretch where some axes get stretched more than others, and then you rotate them back into the right position. So essentially, that you can do this should not seem too weird. After all, if you send some arrows to another set of arrows, those arrows are just longer or shorter, i.e. there's a stretching, and they're at the same angle or different angles, i.e. there's some rotation going on. So this is essentially how all linear maps from Rn to Rm work, a fact that we'll prove today. And essentially, the main thing that we'll show is the following. Oop, I've still got my eraser on. Today, we will show this is true and that an analog of it holds for maps in LVLW for V and W inner product spaces. I should say of finite dimension. I will throw a caveat. I'll leave that there. Of finite dimension. There is an analog of it that we can produce where we can relax that assumption a little bit. But for now, essentially we'll show, hey, look, all linear maps between any two inner product spaces of finite dimension basically just kind of work like this. You rotate, stretch, and you rotate. That's it. And they don't have to be the same rotation. They can be totally different rotations. It just rotate, stretch, and rotate. All linear maps. Bam. Now it suddenly feels easy. Even things like integration, differentiation. Those are linear maps of functions, right? So, crazy. Integration and differentiation are just kind of rotate, stretch, and rotate? Yeah, in a certain sense, that's true. So let's get into it. To do this, we're going to need some facts about the adjoint of t multiplied by t. Okay, so here is what we'll prove. This little laundry list of facts. None of them are too bad, but we'll need them to say the things we want to say. So we'll suppose that t is a linear map from V to W, where V and W are inner product spaces. Then we will take t star t to be a positive operator on V. We'll show that that's true. We'll show that the null space of t star t is the null space of t, that the range of t star t is the range of t star, that is the adjoint of t. And we'll show that the dimension of the range of t is the same as the dimension of the range of t star, which by the previous result is naturally the same as the dimension of the range of t star t, since we've shown those things are equal, right? Okay, let's run through it. Let's start out with part A. Okay, so to remember, to be a positive operator, you have to be self-adjoint, and you have to satisfy operator times vector, inner product with vector, that thing bigger than or equal to 0 for all vectors. Okay, so let's run through it. Notice that t star is equal to, well, t star star, which is t star t. So t star t is self-adjoint. Let me zoom out a teeny tiny bit. Okay, cool. So we've got self-adjointness. Now, if v is a vector in V, then we have the following. T star T V, inner product with V, is equal to, we'll just use the properties of the adjoint to bring that T star over to the other side, and I'll get TV, oops, which notice is equal to the norm of TV squared, which is definitely greater than or equal to 0 for any V. Hence, T star T is positive. That it is a self-adjoint operator that satisfies operator times vector, inner product with that vector is greater than or equal to 0. Okay, cool. So we got part A down. Nothing crazy. Part B, similarly easy. Let's do it. So these are just some facts that we'll need for a little bit later. Don't worry about them too much right now. Don't be trying to overthink what all of these things mean yet. Just basic facts that we'll use to construct the more meaningful thing. So let's just run right through it. All right, let's show that the null space of T star T is equal to the null space of T. So first off, if V is in the null space of T, TV is equal to 0. So T star T V is equal to T star of 0, which is 0. And V is in the null space of T star T. That is, hence, null T is contained in the null space of T star T. Now, suppose that V is in the null space of T star T. Then we have the following. 0, well, that's certainly equal to the inner product of 0 with V. After all, take the inner product of 0 with anything, you get 0. Okay, but the 0 vector, that's equal certainly to T star T. T star T of V, right? Since we're supposing that V is in the null space of T star T, that means that T star TV is equal to 0. Okay, but using properties of adjoints, now I have that this is TV and that this is TV in the second argument as well. So that's the norm of TV squared. So if the norm of TV is 0, then TV is equal to 0 and V is in the null space of T. Hence, the null space of T star T is contained in the null space of T. So, null T is equal to the null space of T star T. That is, we've shown that the null space of T is contained in the null space of T star T. And we've shown that the null space of T star T is contained in the null space of T. So they're equal. All right, nothing crazy there. Let's show that the range of T star T is equal to the range of T star. So let's just do it. Since T star T is self-adjoint by part A here, we showed this already. Okay, we can use our formula for the range of a self-adjoint operator. We have the following. So the range of T star T is equal to the orthogonal complement of the null space of T star T. Which, now notice, we just showed that the null space of T star T is equal to the null space of T. So this is the orthogonal complement of the null space of T. What's the orthogonal complement of the null space of T? Well, it's the range of T star. That's just a fact about adjoints in general. Nice. All right, sweet. We got it down. Okay, let's do D. Part D asks us to show, going back up, that the dimension of the range of T is equal to the dimension of the range of T star, which from part C tells us that the dimension of the range of T is also equal to the dimension of the range of T star T. Okay, so by part C, dim range T star is equal to the dimension of the range of T star T. Okay, nothing crazy. Now, observe the following. The dimension, lagging on me, dimension of the range of T, well, I certainly claim that that is the dimension of the null space of T star's orthogonal complement. Just range of T is equal to the null space of T star's orthogonal complement. Nothing crazy. Okay, but hey, wait a second. We know what the formula for the dimension of this thing is. It is the dimension of everything remaining in W except for the piece that lives in T star. Okay, but wait a second. By the fundamental theorem of linear maps, I have dimension of domain minus dimension of null space. That's dimension of range T star. Oh, so the dimension of the range of T is equal to the dimension of the range of T star. And we already know the dimension of the range of T star is equal to the dimension of the range of T star T, since those two are in fact equal. So we are done. Nice. All right. With this little bit of facts right here that says that T star T is a very nice operator in many different ways. It's got an easy to characterize null space. It's got an easy to characterize range. Its range, we know the dimension of it. It's pretty simple. Cool. Let's get into it and do a little bit more using these facts. Okay, let's get into it. Singular value decomposition probably involves talking about singular values. Here's the whole idea of it. If you've got T, a linear map from V to W, we'll say that a singular value of T, or that the singular values of T, are the non-negative square roots of the eigenvalues of T star T. And in general, we'll assume that they're listed in decreasing order and included as many times as the dimension of the corresponding eigenspace of T star T. So, i.e., if lambda 1 through lambda k are the eigenvalues of T star T, well, since T star T is self-adjoint, these things are automatically real, and since it's positive, they are all automatically non-negative. Okay, great. Cool. So, and dim E lambda I T star T, that is the dimension of the corresponding eigenspace. Let's let it be equal to Ni. Then square root lambda 1 up through dot 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 square root lambda 1. This is repeated n1 times through dot 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 all the way down through the square root of lambda k through dot 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 square root lambda k, and this is repeated nk times. These are the singular values of T, assuming that lambda 1 through lambda k are listed in decreasing order. So here, let me write that in a nice way. So assuming that lambda 1 greater than or equal to lambda 2 and so on all the way down through lambda k. So even if you didn't list them in decreasing order, people would still tend to call them the singular values, but we're just going to assume that they're always listed in decreasing order since, hey, there's nothing wrong with assuming that. You can always do it. It's not really a restriction at all. It's just a convenience. We'll throw it into the definition so we don't have to start a bunch of proofs by saying, like, sort the singular values in descending order. But yeah, there you go. So we'll take the eigenvalues and we'll repeat them as many times as the dimension of their corresponding eigenspace. And we'll take the square roots of them. That's it. All right, maybe these seem weird. I'll tell you what they are. Let me show you. Going back to our picture, when we took this circle and we stretched it, made it into an ellipse, the singular values turn out to be, ooh, why can I not draw here? The lengths, oops, why is this not working there? Oops, there we go. The lengths of the axes. That is how much the circle got stretched and deformed. If you're in like a different dimensional space, like R50 or something like that, then the analog of the ellipse there will have, 50 different axes, major and minor, all can be different lengths. But basically it's the same picture. How much are we stretching out these axes when we make our ellipse? That is what the singular values tell us, and that's how we'll show they work. So here's the role of positive singular values, and here's how it works. All right, let me why am I lagging out here? Okay, proof. There we go. Okay, so a bunch of facts. We'll suppose that T is a linear map from V to W. We'll show that a bunch of nice things are characterized by the singular values. For example, injectivity and surjectivity, as well as the dimension of the range. So that surjectivity and the dimension of the range would be related is very easy to see. Injectivity is maybe less easy to see. So let's prove part A. So a linear map T in LVW is injective if and only if null T is trivial. So T is injective if and only if null T is trivial, but that holds if and only if the null space of T star T is also trivial, which says 0 not an eigenvalue of T star T. And that means, and that's only true if 0 not a singular value of T. Since after all, the singular values are the square roots of the eigenvalues of T star T, right? So if T star T does not have 0 as an eigenvalue, T can't have 0 as a singular value. Okay, so injectivity is characterized fully by singular values. Now let's do B. Okay, for part B, not going to be too bad either. The number of positive singular values of T is the dimension of the range of T. Okay. Using the spectral theorem on T star T, there is a basis of eigenvectors of T star T such that the matrix of T is diagonal with its eigenvalues